Let's talk about frictional forces. There are two types of frictional forces. There is what we call kinetic friction, and there is static friction. Kinetic friction, that's when you have movement. You have two surfaces, and as they go by each other, they rub against each other. That's what the kinetic friction is. Now, to calculate the kinetic friction, we call that F of K. It is mu K times N. And mu K is known as the coefficient of kinetic friction. And that's a constant. You find that in a book. It's a table usually. It says if it's rubber on concrete, it's 0.85. If it's glass on glass, it's 0.42. If it's Teflon, it's 0.06. But these are constant, usually given to us, or to find them, you might see some example today. How do we find them if we do something else to the problem? But if you look at that equation, this equation right here, there's a couple of things about that equation we can notice. So let's call these the rules of for kinetic energy, or kinetic friction. I'm sorry, not energy. That's coming up later. Kinetic friction. If you look at that equation, let's pick a number for mu k. Let's say it's 1. If n is 50, 1 times 50, the friction force is 50. Now what will happen if n becomes 100? What is 1 times 100? That's 100. So notice as the normal force increases, the kinetic friction increases. So that's rule number 1. The kinetic friction force, F of K, is proportional to the normal force. Normal force N. So the kinetic friction is proportional to the normal force. Meaning, if the normal force increases, the kinetic friction will increase. If the normal force decreases, the kinetic friction will decrease. Again, we're talking about like sliding this along that table. If this object is heavier, when you slide it, that friction force is larger. The other thing you'll notice about the kinetic friction, like sliding this on this paper, it's independent of the speed. How fast you're moving is not a factor. So it's independent of the speed. So the speed is really not an issue. How fast you move this, it's not important. And the third thing, it's independent of the area of contact. Meaning, if I lay this flat, the kinetic friction is going to be the same if I put it on its side this way, if I put it on this edge this way, if I put it on that corner that way, and move it, the kinetic friction will be the same. So the area of contact is not an issue. The speed is not an issue. The only thing that will affect the friction force is if the object gets heavier or lighter, which is N. Here's an example. Let's say we have a salt shaker sitting on the dining room table. As for salt, there's the holes in it. And it's sitting there, it's resting, so it has initial speed of what? Nothing. Now, your brother's 0 actually. Your brother said, can you pass me the salt? Instead of picking that and giving it to your brother, you decided to push that. You give it a push and you let it go. You pushed it like this. You pushed it and it went, then stopped. Notice? Just like that. So we give it an initial speed of 1.15 meters per second. The mass of this salt shaker is 50 grams. So it moved in this direction. And when it gets to the spot, stop moving. So now the found velocity here is 0. All we know that shaker traveled a distance of 0.84 meters. So the question now, can you tell me, can you find what mu k is just based on this experiment? And part 2, can you tell me how much time is required if the velocity equals 1.53 meters initial velocity 1.53 meters per second. So let's take a look at that shaker there. When you look at the shaker, here we go, we'll make it small here. The force on it has the weight down, which is mass times gravity. The mass is 50 grams, which is 0.05, divided by 1,000, times 9.8, and that is 0.49 Newton. The table is pushing up on that shaker in that direction. That's the normal force. And since the table is flat, I'm assuming the table is flat, the normal force has to equal 0.49 Newton, just like this one. The question, can you find mu k? Well, there's only one equation that we can use to find mu k. That's the only one we know. And that is F kinetic friction equals mu k times n. I know what n is. N is 0.49. I'm looking for mu k. So if I know what this value is, if I know what that number is, I can solve for mu k. Now, one of the rules I should say here about the friction force, it's always pointing in the direction opposite to the movement. So I should add it to that list really here, which is I forgot to add. Rule number 4, or property number 4. It is parallel to the surface of contact, that's the direction of it, and has a direction opposes its motion. Meaning what? It's backward to the direction the object is moving. I should have put that in. That means here, when the salt shaker was going to the right, the friction force Fk, which is right there, parallel to the surface, right there, and it's pointing backward if the salt shaker is going to the right. So I need to find what f of k is. Again, if I know what f of k, plug it in here, I'm done. How do we find it? Well, we have the object that's moving. We know the initial speed, we know the final speed, we know the distance. So let's write what we know. My goal is to find f of k. But let me list what I know. I know the initial speed, it's 1.15 meters per second. I know the final speed, which is 0. I know delta x, which is 0.84. What else? You know what? I can find the acceleration. How? Using one of those equations. The 5 equations that we had. Zero squared equals 1.15 squared plus 2 times a times 0.84. Zero equals 1.3225 plus 1.68a. Bring that to this side. I can find the acceleration, which is negative because we are slowing down 0.787 meters per second squared. Just from the story there. Why am I interested in that value? What do I care if I know A or not, the acceleration? Let's go back to Newton's second law. If an object is moving, Newton's second law, the net force equals mass times acceleration. Now let's talk about this. You push the salt shaker to the right. Let's define to the right is positive, to the left is negative. Your friction force is backward. That's the only force acting on the salt shaker. Once the shaker leaves your hand, again, here's my shaker, push it. Once I finish pushing, my hand, nothing touching it. The only thing that was affecting it is the friction. So it's 0 forward. There's no force pushing forward. That's the net force, nothing. Minus the friction force. The friction force was backward. It's negative. Should equal to the mass times the acceleration. So negative Fk equals, what was the mass of this? 0.05. The acceleration, we just calculated that 2 seconds ago. Where was it? Negative 0.787. Negative F of k equals negative 0.3935, which means F of k, the friction force, is 0.3935. Now I know the friction force. I said perfect. Let's go back to the first equation we wrote today. We wrote this equation. We said F of k equals mu k times n. Let's write what we know. We know what F of k now, 0.3935 equals mu k times 0.49. Can we solve for mu k? We divide them. Mu k will have to be 0.08 here. And mu k does not really have any units. The reason mu does not have any units, this is Newton, that's Newton. The units have to match on both sides. That means mu k has to be unitless. No units for it. Let's try another one. If you ever been to Disney or to Boston Aquarium, sometimes you watch a show there, they have these sea lions, trained sea lions, and they come on a platform and they slide into the pool. This is like the water here. So we have a sea lion. This is my sea lion. Let me draw it here. We know this board makes a 23-degree angle. Here's my sea lion. It's sitting on the board there. So we have a sea lion slides from rest. Let's use from rest. The word rest becomes crucial. Slide down this ramp. The length of the ramp, 3 meters long. Let's assume the coefficient of friction between the ramp and the seal is 0.26. Assume that. And here's the question. How long, that's time-wise, does it take the sea lion to make a splash? In the pool? How long is it going to take it to hit the water, basically? Now, what I'm going to do here, I'm going to make my axes this way. This is my y-axis, and this is my x-axis. Let's list all the forces that's acting on the sea lion. We know there's a normal force pushing upward in that direction. The sea lion's going to slide down the ramp. That means there's a friction force going in that direction. Kinetic friction. It's moving. And we get actually the weight straight down. Straight all the way down here. But we're going to take that weight and break it down to x and y component, as we did last time. It's going to have a component in this direction, which is mg sine of theta. And this is mg cosine theta. These are my forces. So if I draw, instead of being crooked here, let's redraw my free body diagram. This is x. This is y. Again, we have the normal force pointing upward. I don't know it yet. I have no idea what the value of it. I have this one equals mg cosine theta. We know what m, the sea lion, oh no, you know what? I don't have the mass of it. Okay, m, gravity 9.8, I thought we know the mass. Cosine what? 23 degrees. Theta is 23. So this will be, if you do this times that, it'll be 3.83 M. This one here is equal to mg sine of theta, or sine 23. We know what g, we know sine 23, plug them in. This number is wrong here. This is actually 9.02. That one here is the 3.83 times m. And what else we have? We have the friction force. Now, hopefully the seal wasn't bouncing up and down in this line along the y-axis. It wasn't jumping up in the air. If it's not, then what we know, we have equilibrium in the y direction. The net force in the y direction is 0, which means if you take all the forces pointing upward, they should equal to all the forces pointing down. What do we have pointing upward? We have the normal force, and what do we have pointing down? 9.02 M. That's what that number is. Hard to read. 9.002 M. That's the normal. Okay. We're looking for the time here. Well, the only thing I know so far, when I look at that problem, I know the initial speed of the problem is equal to 0, starts from rest. I know delta x equals 3 meters. And that's all I know. And I'm looking for the time. That doesn't help me. Usually I need 3 things, because every equation we wrote last time has 4 things in it. You need 3 to find the 4th one. So this doesn't really help me. I need one more thing. Well, maybe I can calculate the acceleration of the C line coming down, because if I know what A is, I might be okay to solve it. Okay, how can I find what A is? Well, I need an equation that uses the acceleration. Okay, let's look at the x direction. That's this one. In the x direction, the seal was going to the right. It was coming down, which means to the right. That's what direction was moving. Newton says the net force in the x direction, in this case, should equal to the mass times the acceleration. Well, since the seal was going to the right, so the net force is this force minus that one. This one minus that. This minus this. So it's 3.83 M minus F of K equals the mass, which is what? Unknown, times the acceleration, which is I'm looking for. I don't know what F of K is. Let's go back here. If I know the normal force, and I know mu, notice mu K. If I know this and this, can I find F of K? F of K equals mu K times N. What is mu K? Mu K is 0.26. What is N? N is 9.02 M. Do the math. What's F of K? F of K is 2.35 M. Now that should help me. Why? Because I can take this value and put it right here. So let's look and see. Let's plug it in. So let's plug it in. So 3.83 m minus 2.35 m equals the mass times the acceleration. Notice, since every term has an m in it, I can cancel the m's, because you can divide every one of them by m. And if you divide by m, you end up with 3.83 minus 2.35 equals a, and your acceleration, the seal is picking up speed because it has an acceleration positive value of, what's that value equal to? 1.48 meter per second squared. So now bring that value back with you here. Plug in 1.48 meter per second squared, and let's look at our equation, see if there's one that will allow us to find now what t is equal to. So let's see. I know V0 being 0. I know delta x being 3. I know the acceleration is 1.48 meters per second squared. And I'm looking for the time. How about this equation? X equals x sub 0 plus V0t plus 1/2 at squared. X, or delta x actually, or make it 3 equals 0. If you make the initial value 0, then the final position in 3 meters away, plus V0, which is 0 times t. T is unknown, we're looking for it, plus 1/2 times 1.48 times t squared. 3 equals 0.74 t squared. T squared equals, divide 3 by 0.74, that's 4.05, which means t equals 2.01 second. So it's going to take the seal about 2 seconds to slide down that ramp. Okay. When I started my video today, I said we're going to talk about frictional forces. I said forces with an S. And I said there are two types of friction forces. Kinetic friction, that's the one we've been talking about the whole video. So the other one is called static friction. Let's look at the static friction. And static friction, it's a force that tends to keep two surfaces from moving relative to one another. So basically, what keeps static friction is the force, the friction force that keeps this from moving. Now sometimes when you put a heavy object like an iPhone here, and I push on it a little bit there, it's not moving. The reason, because of the static friction. I move a little bit harder, still not moving, because of the static friction. But eventually I'm going to push hard enough, it's going to force it to move. And that's your maximum static friction. So the static friction really changes. It depends how much you're pushing. So your static friction, we call it F of S. It is between 0 and the maximum value. There's some maximum number. And how do we calculate that maximum value? Well, to calculate that maximum value is going to be equal to mu s, coefficient of static friction, times the normal force. For example, mu s for between the tires of your car and the concrete driveway can range from 1 to 4. Mu s is usually larger than mu k. It takes a lot more to get the car moving. Once it's moving, it doesn't take much to keep it going because mu s is larger than mu f. So an example, let's take this iPhone. We'll say the mass of this iPhone has a mass of 0.5 kilogram. And I really have a nice case on this. I'm having a hard time pushing it there. It's very rubbery there. So let's say mu s for this is 0.97. So the maximum static friction is going to be mu s times n. Well, I need to find what n is. Well, if we know the mass, we know n. N equals mass times gravity. And the mass is 0.5. Gravity is 9.8. So that number will be roughly 4.9, or almost exactly 4.9. So what is the maximum static friction here? It's going to be mu s, which is 0.97, times n, which is 4.9, and that number is actually 4.75 Newton. So let's look at that picture. Let me draw a picture of my phone here. And I need 4.75 to get it to move, to make it move. I'm going to come back. I'm going to talk about these two equations. So if this is my iPhone here, this is my iPhone. You saw it's black. I will need, so Fs maximum, it's 4.75. So if I push on the iPhone, if I push with the force, that's me pushing with my finger, of 1 Newton, is that phone going to move? The answer is no. I need a value larger than this to make it move. So I'm pushing on it in that direction. That means there's a static friction force pushing backward, F static. And how big that value? It's equal to this. Has to be equal to it, because if it's bigger, it's going to make it move in that direction. The same iPhone, if I increase that force, so this will not move. If I increase that force to 2 Newton, is my iPhone going to move? No. So there's a static friction pushing backward, blocking me from moving, and the value of that's also 2 Newton. If I push on it with 3 Newton, is it going to move? No. And there'll be a static friction equals 3 Newton. If I push on it with 4 Newton, if I push on it with 4 Newton, is the iPhone going to move? No. There's a static friction of equal 4 Newton. If I push on it with 5 Newton, notice this is larger than that. It will force it to move now. It will move. And we do not have a static friction now. We have what? Kinetic friction. We have a kinetic friction equal to that value and pointing backward. So here will not move, not move, not move, not move, finally will move. You need a minimum of 4.75 to make that iPhone move. So notice the value of the static friction could be any number, anywhere between 0 and the maximum value. It depends on that pushing force. So let's write rules about static friction, just like the other one. Rules of static friction. We know the static friction, let me just write it down, between 0 and Fs max. And I know Fs max, to calculate that, is you need mus times n. So looking at these equations, rule number 1, it tells me that the static friction F of S can take on any value between 0 and Fs max. Could be any number. And just like the kinetic one, it is independent of the area. So it doesn't really matter if we put that iPhone flat like this, on its side this way, standing up this way, on that corner, still going to be the same value. And again, the other thing, we know the direction of it. The static friction F of S is parallel. I forgot to write that on the previous one when I added it, to the surface of contact. And has a direction opposes the relative motion. If it was the object to move, because you're pushing on it, it's going to be pointing in the direction backward to it if it's going to move. So these are the properties of it. Let's take an example on this. Let's say you're moving furniture there. And you know when you have these trucks, they have these ramps on them. They look like this. On the back of the truck, they have this ramp that it helps you carry the stuff down. I have a box, a piece of furniture, could be a nightstand, it's a big piece, there we go. Dresser, 3 drawers, 4 drawer dresser. And you want to move it, it's a big box there. It has a mass equals, 95 kilogram, over 200 pounds. But heavy, but 220 pounds. And we notice that box does not slide, so there's an angle here. It does not slide till this angle exceeds, let's say 23 degrees, pick some crazy number. So here we go. The box starts to slide when the angle exceeds 23 degrees. Can you find mus? So we're talking about the box not sliding. 23, the box not going to slide. A hair over that will start to slide. So let's put my axes here. This is my y-axis perpendicular to that. This is my x-axis. So my forces, this is on incline, remember that, just like the other ones. This is going to have a value in this direction of mg sine 23 degrees. It's going to have a value in this direction. Mass is 95. mg cosine 23 degrees. It's going to have a value in this direction. That's the static friction, F of S. It's going to have the normal force, upward, N. And these are the only forces acting on the box there. Now let me redraw that and make it a little bit cleaner because it looks a mess there. So there's the box, right here, I shrunk it. So we have, in the x direction, mg sine of 23. Let's see, mg sine 23. Do the math. I probably don't need it, but that's 364. I have mg cosine 23. Do the math again on this one. 857. We get the normal force pushing upward. And we get the static friction, F of S, which is mu s times n, pushing in that direction. Now at 23 degrees, we said the box is not moving. It's stationary. That's known as equilibrium. You'll see that in the next video. When the box is not moving, that means we have, if you look at the net force in the y direction, has to be 0, which means take all the forces pointing upward, should equal all the forces pointing down. What do we have pointing upward? Pointing upward, we have what? N. And what do we have pointing down? 857. That tells me what the normal force is. Also, if the box is not moving, we have an equilibrium in the x direction. That means all the forces pointing to the right should equal all the forces pointing to the left. What do we have pointing to the right? To the right is what? 364. And what do we have to the left? F of S. So now I know what F of S. We said F of S equals mu s times n. So 364 equals mu s times n. I'm looking for mu s. We know what n is right here. Mu s equals what? 364 divided by 857, which is 0.42. And that is the end of that.